So far in the course, in all the lectures that we have come across so far, we have been majorly looking at transmission lines from different angles. All of those discussions are based on one undisputable fact, that in general, in a transmission line, there exist two waves, one forward wave and one backward wave. So, as an extension of this, we said that the voltage at any point on the transmission line is found as a superposition of these two waves. So, that is like saying the voltage at any point on the line L, let us say it's a lossless line, then this is given as V plus e raised to j beta L plus V minus e raised to minus j beta L. So effectively, the voltage is obtained as a superposition of the incident wave and the reflected wave, which is also known as the forward wave and the backward wave, respectively. The question now is this always true? Is this always true? Obviously, it is not true at all times. This expression is merely a steady state solution. That means when the transmission line setup that consists of the source, the line and the load that is existing or in the on state for a very, very long time. I am talking about this very simple setup. This is on for a long time. In reality, what happens is at the time when the source is switched on, the wave starts propagating from the source towards the load. And as you know, every wave has a certain velocity. Every wave has a certain velocity, and therefore the time it takes to travel from the source to the load is finite. So let us say if the length of the line is some capital L and the wave velocity is some v, then we define something called as the propagation time. From the source to the load, that is, let's say it is Tp, which is nothing but the length of the line divided by the velocity of the wave. So in reality, what happens is this wave takes some time to hit the load, and until such time, that is, so long as t is less than Tp, only incident wave exists, or only forward wave. This wave exists. Now, until and unless the wave hits the load, there will be no reflection. So, reflections or the backward wave originates after t becomes equal to Tp or more. So, once there is a reflected wave after t becomes more than Tp, then in that case, this wave starts traveling to the left and hits the source. Again, so far we have assumed that the source is ideal. We conveniently did not talk about it. But when the reflected wave goes back and hits the source, what would happen? Again, there may be some reflection depending on what the impedance of the source is. And then again, there will be some wave that is coming back towards the load. So, therefore, all said and done, we see that merely looking at the transmission line voltage expression that we have worked with so far and what you have learned during your basic waves course also, although that is very useful, this is a steady state solution and therefore does not often give a very clear picture that helps us understand the transmission line behavior in a 100% clear sense. So therefore, in today's lecture, in this particular lecture, we shall look at the transmission line but from a time domain perspective, that is from a transient perspective. So for doing this, we have to first see the line in totality. That is, we have to look at the source also. Now, if this source is an ideal source, it's an ideal voltage source, then that means the impedance of this source is essentially 0. So therefore, if there is a reflected wave, it hits the load, it hits the source, then in that case, at the source end, there will be a reflection with reflection coefficient of 1 or rather -1. So therefore, a wave will come back and again travel towards the load whose magnitude will be equal to the wave that was incident on the source back. So therefore, effectively what is happening, we can see from a very abstract sense, is that this propagation from left to right, then right to left, again left to right. So therefore, this is a never ending phenomena. So effectively, there are multiple such reflections. There are multiple such reflections which are actually happening in the transmission line. Furthermore, we have assumed so far in the lectures that there is a wave which is traveling, or there are two waves which are opposing in nature, and we have conveniently assumed that those are sinusoidal in nature. The waves are sinusoidal, and that is good because in reality most waves are sinusoidal, and if they are not sinusoidal, then as per Fourier's theory, we know that any possible mathematical function, a voltage function, can be realized as a sum of finite number or infinite number of sinusoids. So therefore, our assumption of sine wave is actually not a bad assumption. But just to look at the transmission line from a different perspective, that is the time domain perspective, we will assume a slightly different nature of the source, just to show you that the analysis, even with different assumptions, would ultimately boil down to a very simple solution, and that is not very different from what we have essentially been working with in the lecture so far. So therefore, assume that it is a unit step source. That is u of t, which looks kind of like this. Until 0, for minus axis, time axis, the voltage is 0, and exactly at 0, this becomes 1. This is what I mean by unit step. Then let us have a realistic source where the source impedance, that is Zs, is 100 ohms, and we shall also assume that the load impedance ZL is 100 ohms. and the transmission line that is connecting the source and the load has a characteristic impedance Z0 of 200 ohms. And most importantly, the propagation time from one end of the line to the other end of the line for the wave is Tp. Well, so with this, let us draw what the line and load setup along with the source would look like. This is my unit step source U of t, and let us say it has a source impedance Zs, and there is a load also, that is ZL, which is 100 ohms. Zs is also 100 ohms, and there's a transmission line having two conductors connecting the source and the load, whose characteristic impedance Z0 is 200 ohms. Let us say, for the sake of simplicity, that the second conductor is essentially ground. The second conductor is essentially ground. And let's label these points. This is point A and this is point B. Now, one thing that we can assume is that the line length is L, and this L is much more than any other dimension or circuit component. That means it is much bigger than the resistor, the source, the load. So therefore what we will assume is that the time taken for the wave to propagate from the source end to point A is negligible. Okay, so therefore, just to make life easier, we can redraw the circuit in this way. This becomes point A, and this is point B, which has the load. This is what it is, and the line has some length L with propagation time Tp with the characteristic impedance of 200 ohms as assumed. So now the question is, using this setup, what can I say about the load voltage? What will the load voltage look like as a function of time if the source is a unit step? So therefore, let us look at this particular setup from a time perspective. So let us say I am switching on the circuit at t equal to 0. Our source becomes on. So if the source becomes on at t equal to 0, Zs is 100, not 200. So if the source becomes on at time t equal to 0, the wave launches from the source very quickly reaches point A. So what will happen? Let us say t equal to 0 plus, that is at a time which is very negligibly above 0, we'll say wave reaches point A. wave reaches point A. Now what is happening? Now, what will be the voltage at point A? So let us say at this time, what will be the voltage at point A with respect to ground? Will it be the same as the source voltage? Let us say this is 1 volt. Well, notice that A is a very special point. That is the point at which the source is essentially ending and the transmission line is starting. So therefore A is a discontinuity. So therefore we now have to ask, what is the impedance that is seen by the transmission line, or the impedance that is seen by the wave which is at point A and it is about to enter the transmission line? Has it reached the load yet? No, because the time is frozen currently at t equal to 0 plus. So therefore the impedance seen by the wave is nothing but the characteristic impedance of the line itself. Because as you know, the definition of characteristic impedance is the impedance seen by the wave which has not yet reached the end of the line. So therefore, the wave is seeing an impedance of 200 ohms. So it's like saying the circuit would become something like this: 1 volt, 100 ohm, this is ZS, and the impedance of the line would look like this, and this is essentially VA. This is at t equal to 0 plus. So therefore, VA at time 0 plus would essentially boil down to a voltage division ratio, that is 200 divided by 200 plus 100. So that is 1 volt into 2 by 3, which is 2 by 3 volt. Is it fine? So at time t equal to 0 plus, or for all practical purposes t equal to 0, the voltage at point A is 2 by 3 volts. We have calculated this. Now what happens? Now that the voltage over at point A is clear, the wave can start traveling towards the load in peace, and it will travel as it is to point B without any change. Why? Because this is a lossless transmission line. So this 2 by 3 volt will reach point B. After what time? After time Tp. So I'll say at time t equal to Tp, wave of amplitude 2 by 3 volt reaches point B. Now what is happening? Now the wave is hitting this load. The wave is hitting this load. So therefore, what will happen? Now some reflection will happen. So then what will be the reflection? So at point B, the reflection coefficient is gamma L, and that is nothing but ZL minus Z0 divided by ZL plus Z0. So that is 100 minus 200 divided by 100 plus 200, which is minus 1 by 3. So therefore, I can now write at the load, or at point B, I'll say incident voltage is 2 by 3 volts, and the reflected voltage will be gamma L into 2 by 3. So that is nothing but we derived gamma L is minus 1 by 3. So this will be minus 1 by 3 into 2 by 3, which is minus 2 over 9 volts. So therefore, VB, that is the voltage at point B at this time, T equals TP. How much would the load voltage be? Load voltage is nothing but the sum of incident and reflected voltage as per the transmission line theory. So therefore, incident is 2 by 3 and reflected is minus 2 by 9. So 2 by 3 plus of minus 2 by 9. How much does that come out to be? That comes out to be 6 by 9 minus 2 by 9, that is 4 by 9 volts. So this is the voltage VB, or that is across the load at time t equals TP. Is that fine? So far we have analyzed what are the voltages when the wave is traveling from left to the right. Now we just proved that a reflected voltage of minus 2 by 9 starts back from right to left. So that's like saying if the load is here and we have the source over here, this is point B, this is point A, this is ground. So now this reflected wave of magnitude minus 2 by 9 volts starts going from right to left, and it will again travel undiminished to point A. Why? Because as always this transmission line is lossless. So therefore this reflected wave will now reach this point A at what time? Time t equals 2TP. Because just like how the forward wave takes time TP to go from A to B, the reverse wave or the backward wave or the reflected wave would also take the same amount of time, because the length of the line is not changing. That is TP time to travel from point B to point A. So if the reflection happened at t equals TP, then the reflected wave will reach point A at time t equals 2TP. So now if this wave hits the source, what will happen? Again, some reflection will happen at the source end. So I can now say gamma S, that is reflection at the source side, or reflection coefficient at the source. What would the formula be? Just a converse of the load reflection coefficient, that is Zs minus Z0 divided by Zs plus Z0. And how much would that be? It will be the same as gamma L, which is minus 1 by 3, because Zs is 100 and Z0 is 200. Right? So therefore, at time t equals 2TP, I am looking at point A. So over here, the incident voltage is minus 2 by 9, because this is the voltage of the wave that is going from right to the left. So this is incident. And the reflected voltage is how much? Gamma S into minus 2 by 9. That is minus 2 by 9 into minus 1 by 3, which is 2 by 27 volts. So therefore, I can say VA at time t equals TP is what? The sum of these two, that is minus 2 by 9 plus 2 by 27. How much would that be? That is minus 4 by 27. I'm sorry, minus 6 by 27 plus 2 by 27, which would mean minus 4 by 27 volts. I hope this is correct. Yes, it is correct. So this is the voltage at point A at time t equals 2t when the reflected wave comes. So now, after this 2 by 27 volts would again start going to the right, and then it will hit B. Now similar things will happen at point B, what happened over here. So therefore, as you can see, this is a never ending phenomenon. So therefore, what we can do, we can represent this in the form of a diagram. So what we are seeing essentially is that there are multiple reflections. It's almost as if the wave is contained within the transmission line and keeps bouncing here and there. Left to right, right to left, again left to right, right to left. So it's almost as if the wave is bouncing around from left to right. So therefore, let us draw this phenomenon. Let us say this is point A and this is point B. Point A is after the source and point B is at the load, as we have proved. And let us draw the time axis. In a vertical manner. So let us mark some important points like 0, TP, 2 TP, 3 TP, 4 TP, 5 TP, and so on. Now we have derived, suppose I am essentially denoting this point A and point B as two dashed lines for better clarity. Then at time t equal to 0, what is the voltage at point A? We derived that at time t equal to 0 or 0 plus, the voltage at point A is 2 by 3 volts. So it's like saying a wave is launching over here with magnitude 2 by 3 volts. And the wave will reach point B at what time? Tp. This was the first journey. As you recall, this was the first journey of the wave, because at t equal to Tp, the wave of amplitude 2 by 3 volts reaches B. So therefore, at this time, Tp, we have to look at the load. So it's like saying the wave which is starting from point A would reach point B like this. Right? So this wave is now traveling and it has reached point B. Now we had derived at point B also there is a reflection. This reflection at point B, but the voltage at point B at this time we had derived it as 4 by 9 volts. And the wave which is starting over here from the load, it has a magnitude of minus 2 by 9 volts. This is the wave which is starting from the load towards the source. And what time does it reach the source? It reaches the source at time t 2t. So therefore, this is what happens. So just a few minutes back, we proved that the reflected voltage, which again goes back from the source to the load, has a magnitude of 2 by 27 volts. But the voltage at point A now, because of the contribution of this reflected wave, is minus 4 by 27 volts. Notice that at this time t equal to 2 Tp, at point A there are two waves. One is due to this reflected wave, the other is because of the source which is still on. So don't forget that the unit step source is still on, so therefore these two are individual contributions because of different sources and therefore must be added up. Likewise, the 2 by 27 volt wave will reach the load at 3 Tp. So once again, you can do the analysis. 2 by 27 is the incident voltage and the reflected voltage is 1 by 3 into 2 by 27. So therefore, the voltage at point B will be the sum of these. So 2 by 27 minus 2 by 81 will be 4 by 81 volts. Once again, the reflected wave from here will come to the source side . And likewise again, this will go from the source to the load. So the question is, can we again calculate what is the voltages at each of these points? Well, it's not very difficult. So the reflected voltage at this point at 3 Tp is minus 2 by 81. Because it's minus 1 by 3 into 2 by 27. So at this point, the reflected voltage will be minus 2 by 81 into minus 1 by 3, that is 2 by 243 volts. And the voltage at point A will be minus 2 by 81 plus this. So minus 2 by 81 plus 2 by 243, that would be minus 4 by 243 volts. This is at this point. Likewise, I leave it to you as a very simple exercise to prove that at 5 Tp, when this wave comes to the load, or in fact it's so simple that let's actually do it. So the reflected voltage would be 2 by 243 into minus 1 by 3, that is minus 2 by 729 volts. So therefore, the sum total of these two opposing waves at point B at time 5 Tp would be what? It would be incident voltage, that is 2 by 243 minus 2 by 729. The algebraic sum of these two. So therefore, what will this be? I can say it is 6 by 729 minus 2 by 729, which is 4 by 729 volts. So what you can see is that the phenomena which we were seeing analytically earlier, we have now captured it in the form of a uniform diagram. Now, as time progresses, there will be more and more reflections. But immediately I can say that we need not consider those reflections in great detail, is because what you are seeing is that the strength of the waves after all the reflections, essentially they are decreasing. So therefore, beyond a point, they will become negligible. So we don't really have to sweat it out and calculate those reflection coefficients any further. So this diagram which sort of shows that the wave is essentially bouncing from left to right. This is called as a bounce diagram. And this is a very, very important concept. So once we have the bounce diagram ready, let us not forget what was the initial problem we were solving. We were initially trying to solve for what would be the voltage at the load as a function of time. So if the input is a unit step signal, then what would be the voltage at point B as a function of time for the load? So therefore, let us now try to represent the voltage as a function of time. So let us say this is t and this is u of t. So therefore at time t0, this goes to 1. This is the source voltage. This is 0. Now let us say load voltage. Time t equals 0. So let us refer the bounce diagram for this. At time t equal to 0, there is nothing at point B. So therefore, the voltage at the load is then 0. Now, the first instant of time when the load sees some voltage is at time t equals Tp. So therefore, let's mark this point, time t equals Tp. So if time t equals Tp, the load voltage is 4 by 9 volts. So therefore, this will immediately jump up to 4 by 9. And it will continue to be like this. Till what point? Now this voltage stays unchanged until 3 Tp, when there is the next change at the load voltage. So if I now say this is 2 Tp, 3 Tp, 4 Tp, 5 Tp, and so on. At 2 Tp there is no change. The next change at the load happens at 3 Tp. Now the question is, at time 3 equals 3 Tp, what should the load voltage become? At time t equals 3 Tp, what should be the load voltage? Well, what we saw was at time t equals 3 Tp, the voltage at this point is 4 by 81. So the load voltage will be 4 by 81 volts. Is that correct? No, it's not correct. It is not at all correct. Let us not forget the bigger picture. Let us not forget the bigger picture. This 4 by 81 is caused due to the second reflection from the source end. But let us not forget the first reflection which happens at the load. That is, when this phenomena is happening, the unit step source near point A is still on. So therefore, at an earlier point of time, this would have happened, and this at the same time is still happening. That is, at time t equals 3 Tp, what is the load seeing? The load is seeing not only the reflection from the source, but also the main wave that is coming from the source. So therefore, effectively, at this time, it is a superposition of the wave from the source, which is coming unhindered. This wave does not know that it's going to observe a reflection over here, but this portion of the wave has already been reflected a couple of times and gives this 4 by 81 volts. So therefore, at time t equals 3 Tp, the effective voltage at the load will be a sum total of these two. That is 4 by 9 plus 4 by 81. How much is that? So 4 by 9 plus 4 by 81. That is 36 by 81 plus 4 by 81, which is 40 by 81. So which will be slightly above this actually, if you look at your calculator. And it will continue to be unchanged until 5 Tp. Again at 5 Tp, what is happening? At 5 Tp, this voltage 4 by 729 is happening because of 1, 2, 3, 4, 5. 5 times the wave has gone back and forth. But at the same time, a later portion of the same wave is undergoing reflection at this point. And a further later portion of the wave is undergoing a reflection at the same point. So therefore, at time t equals 5 Tp, the voltage across the load will be a sum total of all of these. So this is Vb at time t equals 3 Tp, whereas Vb at time t equals 5 Tp would be a sum of 4 by 9 plus 4 by 81 plus 4 by 729. And this, if you solve, it will be something like 364 by 729 volts, which is slightly above 40 by 81. Right? So what are we seeing? What we are seeing is that as time increases, this voltage essentially converges to something very close to 0.5 volts. The load voltage essentially converges to 0.5 volts. So what is so special about this 0.5? Let us not forget what the initial arrangement was. The initial arrangement was something like this. So what we are seeing is, for time, so let us say VL, or let us say VB, sorry. So VB for time t tends to infinity converges in general to about 0.5 volts. We can actually prove this. How? We saw that the load voltage VB is, for time t tends to infinity, 4 by 9 plus 4 by 81 plus 4 by 729 and so on and so forth. So if we are observant enough, we will see that this is essentially a geometric progression where we can represent it like this: a summation from n equals 1 to infinity 4 over 9 raised to n. So we can take the 4 common, and applying the geometric progression formula, we can say that the sum is nothing but 1 by 9 divided by 1 minus 1 by 9. So that is 4 into 1 by 9 divided by 8 by 9. So these two cancels out. This will be 0.5 volts for a long time. So what is happening is that once the voltage over here becomes 1 volt, after long time, the steady state voltage essentially becomes 0.5 volts. So it is like saying, it is as if after a long time, the transmission line is not playing any role. The transmission line is not playing any role because now at this point, the circuit essentially boils down to a simple potential divider, each of resistance 100 ohms. So 1 volt, 100 ohm, 100 ohm, the voltage across this 100 ohm would be 0.5. So this is a very interesting case. A unit step signal which has a disturbance at time t equal to 0 behaves almost like a DC signal or a DC function for time t much more than 0. So therefore it is like saying that transmission line is not playing any role because there is no wave. A DC voltage is not really a wave. It is simply a constant function. So therefore, no matter how small or how large the line is, the voltage will always settle to 0.5 volts for time which is much more than 0. So what we are seeing is, using our knowledge of transmission lines, in today's lecture, we saw that the load voltage can essentially be calculated by doing a transient analysis, a time domain analysis, where we see multiple reflections back and forth and we essentially add them up. Now, the reason for me taking a unit step is that it is almost like a DC signal which has a small disturbance at one instant of time and is constant at all other points of time above 0. So therefore, you can do this analysis using sine wave also. No problem. But since sine wave is a continuous function of time, the analysis will become a lot more tedious. So therefore, by choosing a very convenient wave or a very convenient voltage function, we saw how using the transient analysis we can derive the voltage across the load. The good part is that you can do this for different kinds of source and load impedances. For example, if the source impedance is 100 ohm and the load impedance is 300 ohm, you would see that the steady state voltage across the load would be 3/4 volts, not 0.5 volts. So this is how essentially we are back to proving that for constant voltages or DC voltages, the transmission line is effectively not playing any role whatsoever. So this is a very important concept, and also the diagrammatic concept of the bounce diagram, which are very important, and we shall revisit the bounce diagram very shortly after a few more lectures. Thank you.